Welcome to BC Video 9.3a Part 1, the integral test. Okay, so these are tests, and it's important you understand in 9.3, these tests only work for series with all positive terms. So they do have to all be positive terms, and we are going to see the integral test and the p-series / we'll get to the harmonic. So we're going to talk about the integral test. It is a rare test. It's not an easy one. It's time consuming. And if you were given a choice, I would leave this one till the very, very end. But of course, there are times when they will say, if the integral test is used, blah, blah, blah. Okay? So if we start off, for example, with this series right here, n plus 1 over n, your an is n plus 1 over n. So what we're going to do is we're going to look at it as a function, f of n, or f of x, whichever you wish to prefer. Okay? So if my function is positive for all x greater than or equal to 1, and all you have to do is kind of write out the first few terms, convince yourself that it's positive, you don't have to prove it. If that function is continuous, now it's going to be continuous, of course that goes back to all the, if it's a polynomial function, it's continuous on its domain, which is all real numbers. If it's a rational, radical, or trig function, it's continuous on its domain, which will depend on what the situation is. So you have to convince yourself the function's positive everywhere for x greater than or equal to 1, continuous, and decreasing. And the easiest way to show that f is decreasing is to show that f prime is always negative. So if those three conditions are met, then the series an and the improper integral 1 to infinity of f of x dx either both converge or both diverge, which means if these three conditions are met, if you find the value of this improper integral, if it converges to a particular number, then your corresponding series over here will converge, not to that number, but you know it'll converge. If this improper integral diverges, it equals infinity or negative infinity, then the series will diverge. So if you look at, let me pause for a second. Okay, so if you look at page 622, which is this page right here, and we are looking at numbers 1 through 24. Let me make that a bit bigger. Okay, it says in exercises 1 through 24, confirm that the integral test can be applied to the series. So remember, we have to show that the corresponding function is positive, is continuous, and is decreasing the whole time for n element of 1 through infinity. It says if it can be, confirm that it can be used, so it can be used. They're just asking you to confirm that it can. Then use the integral test to determine the convergence or divergence of the series. Notice they do not ask you what it converges to if indeed it does converge. So here's number 2. Summation n goes from 1 to infinity. Pay attention to what that lower limit of summation is, of 2 over 3n plus 5. So we let f of x equal the corresponding function, which is 2 over 3x plus 5. All those terms are positive because, of course, x is greater than or equal to 1. So just state that. F is a rational function continuous on its domain, which is everything everything except negative 5/3, but we're fine because our domain is greater than or equal to 1. And now to show that f is decreasing, I'm going to find the derivative, which is why I rewrote it this way, and then the derivative of that is negative 2, 3x plus 5 to the negative 2 times 3 by the chain rule. And that'll end up giving this. So f prime is always negative because the denominator is a square, which will be positive, and the numerator is negative. Therefore, f is always decreasing. So we can use the integral test now. So the integral test is the integral from 1 to infinity of our corresponding function 2 over 3x plus 5 dx. Now you can think that you're going to, in your mind, you're going to let u equal the denominator. Sorry. So du is 3 dx. You'd have to introduce the 3 counteract with a third. I'm going to pull that 2 on the outside times 1/3. And now I'm left with 1 over u du, which is ln absolute value of u. I'm integrating from 1 to, you can't write infinity. You have to rewrite the infinity as limit as t goes to infinity. And then you're going to evaluate that from 1 to t. Okay, so we end up, if I plug in, this is just me showing you how to do this. Okay, so if I plug that in, I'm going to get 2/3, and then limit as t goes to infinity. And don't forget, you need to change this to limit. You cannot leave this as infinity. You have to put a constant there and say the limit as t approaches infinity. All right, so I'm going to plug in t into that expression, minus, and then I'm going to plug in 1. I'll get ln of 8. And what happens is, as t goes to infinity, the limit of the ln of 3t plus 5 goes to infinity, which means it diverges. And if that improper integral diverges, it means that this series diverges as well. So every once in a while, I'm going to recap all the different things we know. So far, testing for convergence or divergence of a series, AN. There's the nth term test for divergence, which states that if the limit as n goes to infinity of AN is not 0, then the series AN is divergent. If that limit is 0, then there's no conclusion. Given the sequence of partial sums, rare, then if the limit as n goes to infinity of Sn is equal to some number L, then the corresponding series converges to that number L. And of course, to find An, there's your formula, Sn minus 1. Okay, the integral test, you let An equal f of n. F of n you have to show is positive, continuous, and decreasing. Therefore, the integral from 1 to infinity of f of x is what you'll be looking at. If that converges, your series converges. If that diverges, your series diverges. And geometric series, if you can confirm that you actually do have a pure geometric series, then what you're going to do is you're going to write out the first few terms, convince yourself it's a geometric series, find the value of r. You're going to state it's a geometric series. You're going to tell me what r is equal to, and then you're either going to say, since the absolute value of r is less than 1, the series converges to a over 1 minus r, which is first term over 1 minus common ratio, or if the absolute value of the common ratio is greater than or equal to 1, the series diverges. Okay, now we're going to go to page 625. Okay, so 625, at the end of every section's homework, they're going to have a mixed bag where they get you to review everything they've taught up to that point. So this is all the different tests, which at this point would be nth term, geometric, P series, etc., although I haven't gotten to P series. Okay, so here's number 88. Write out the first few terms. You can tell you're not multiplying by something to get to the next term and the next term, so it's not geometric. So what we're going to do is we're going to try the nth term test for divergence. We're going to look as the limit as n goes to infinity of 1 over n times the square root of n squared minus 1. Infinity squared is infinity. Minus 1 is infinity. Square root of infinity is infinity. And infinity times infinity is infinity. And 1 over infinity is 0. So there's no conclusion for the nth term test. At this point, unfortunately, we only have one test left to try, which is the integral test. So we're going to let f of x equal the corresponding expression, but with x's. Are all the terms positive? Yes, they are. Is the function continuous on the interval, which at this point is everything to the, we don't have one. So it is a positive everywhere. It is continuous because it's a rational / radical, continuous on its domain, which is less than -1 or bigger than 1. And sure enough, ours is actually bigger than 2 because it starts at 2. Is it decreasing? So your choice, you can either show it the old-fashioned way by showing the ANs are greater than or equal to the AN plus 1s, or you can show that the derivative is always negative. Okay? All right, so we're going to assume, I'm sorry, I keep yawning. We're going to assume that all this works out perfectly, and therefore we can use the integral test. So we're going to do the integral from 2 to infinity. It's very important that it starts at exactly that number right there. So it's 2 to infinity of the corresponding function 1 over x square root of x squared minus 1 dx. This is actually already set up an inverse secant situation, and it'll be the inverse secant of x from 2 to infinity. Now, here's where people mess up. Here's secant. Okay, the inverse secant of a positive is always going to be in the first quadrant. Okay, inverse trig function of any positive quantity will be in the first quadrant. So you can see if you look at the graph of secant that in the first quadrant, the place where it's approaching positive infinity is going to be pi over 2. And then minus the inverse secant of 2, which is the same thing as the inverse cosine of a half, which is your 60 degrees, or pi over 3. So pi over 2 minus pi over 3 is actually pi over 6. So the limit as a approaches infinity of pi over 6 is pi over 6. So our our improper integral does converge, which means our series converges. It does not converge to pi over 6, but it converges.